Well, this is the second of 3 videos on alcohols, ethers, and epoxides. And in the first video, we just looked at the naming and properties of alcohols. But in this one, we're going to look at just the polar reactions of alcohols. Not all reactions of alcohols. There are some oxidation reactions that alcohols can undergo. But we're just going to focus on the polar reactions. So to do that, I really want to sort of draw out that we're going to see that alcohols have a lot of similarities with alkyl halides if we are in acid conditions. So if we have an alcohol in acid conditions, we tend to see some reactions we've seen in the past for alkyl halides. We see some similarities. We see similar reactions to what we've seen with alkyl halides. We see for alcohols if they're in acid conditions. So I'm going to sort of point that out over here on the right, that alcohols with inorganic acids, sulfuric acid, hydrobromic acid, hydrochloric acid, those are inorganic acids. Those are strong acids. Strong acids always react with organic molecules in such a way that they give up a proton to the organic molecule. So that oxygen in the alcohol is going to be protonated, and after it's protonated, if the strong acid is a halogen-containing acid, you typically have SN2 or SN1 reactions. If the strong acid that's mixed with the alcohol is a non-halogen containing acid, meaning sulfuric acid, not having a halogen, bromide, chloride in it, you tend to have E1-like or E1 reactions. So that's what we're going to focus on in this video, was those reactions with non-halogen containing acids, halogen containing acids, and then we'll finish up with just a brief discussion on the products that you'll see if you use not an acid that's a Bronsted acid, but these Lewis type acids where the oxygen in the alcohol can attack the phosphorus, or the oxygen in the alcohol can attack the sulfur, where the sulfur and the phosphorus in a Lewis way are accepting the lone pairs. Remember, the Lewis definition is the acid accepts the lone pair and the base donates the lone pair, but we don't have a proton transfer. So these are going to be Lewis type acids that we'll look at the reactivity of when we mix them with alcohols. And there's going to have to be no water present. Very important. It's going to change some of the dynamics as far as products that are formed. All right, so let's draw out again just the comparison and similarities between protonated ROHs and alkyl halides. So protonated ROHs react like alkyl halides. Remember back to sort of your first semester organic chemistry, if you had a chlorine and let's say an ethyl group and you mix that with a strong base, you can have that nucleophile, that strong base, attack the carbon in a sort of SN2 style where this breaks away. Or we can have more of an E2 reaction where it's attacking those beta protons, beta elimination, where you attack the beta proton, the electrons in that CH bond go to a CC pi bond, and this breaks away. So just sort of kind of reviewing a bit here on what you've seen with strong nucleophiles reacting with alkyl halides. All of that was hinging upon the fact that chlorine had to be a good leaving group. So I've kind of written that in just in, I guess, acronyms here. GLG, it had to be a good leaving group for this alkyl halide to have any of this reactivity with the nucleophile. Well, what we're going to do is have something much like the halogen, just made from an alcohol. We can't have just an OH there because that's not a GLG, a good leaving group. But if we protonate it, this becomes a water molecule. It's not the best leaving group, but it's still a good leaving group. Water can break away. Now it can break away in a SN1 situation where this breaks away first and then this comes in, or it can be SN2 and this breaks away at the same time. In the same manner, we can have, if we consider the E1 reaction, attack of a beta proton, this can come off first and then we attack it. Or we can attack it while this is coming off. Well, we typically don't see that E2 reaction. We typically see E1, or what we'll talk about later on is E1-like. So we typically see this come off first, and then the hydrogen slides over. You get all those things as far as rearrangements and such that come with E1. So typically this will break off first, and then the nucleophile will come in and attack a proton if we're going to have elimination. It'll usually be E1 or E1-like. So what are the differences for these reactions? Well, protonated ROHs certainly require acid conditions. You can't get the proton on to make a water molecule unless you have a strong acid. Well, if that's the case, then our nucleophile must be a weak base. So I've written that in already. This must be a weak base. Why? Because we have to have an acidic proton. If it's a strong base, it'll just grab the acidic proton. That's not what we need up here. Halogens on the alkyl halide are ready to go. They don't need any protonation, so we can have a strong base or a weak base. Strong or weak base for these. And of course we need it to have either basicity or polarizability, but we don't have to have acid conditions up here. We do here. We have to have protonation of the OH group if we're going to have it be a GLG, a good leaving group. All right, here's one more thing too. Given that we are using alcohols as a reagent, it can also work almost as a solvent. They're giving us a protic environment, so SN1E1 reactions tend to be a little more favored when you're dealing with an alcohol for some substitution reaction or elimination reaction in comparison to an alkyl halide. No protic behavior property, not going to have hydrogen bonding and such. So we may see with secondary ROHs more SN1E1 chemistry because the alcohol that's not reacting around the alcohol that is reacting can be of support for carbocation formation. Well, that causes some difficulty because not all secondary alcohols go SN1E1, but just know that there can be a greater tendency to do that compared to a secondary alkyl halide. Secondary alkyl halide where no water is present, solvent's aprotic, you can tend to see more SN2. All right, we have a little rubric, or I have a little rubric. Kind of sets two hemispheres, and we have sort of the brown and the green here. I guess the orange-brown here represents the side of the hemisphere of reactions involving protonated alcohols wherein we have a halogen-containing acid. The acid proton's been given to the OH. It's now a reactive form of the alcohol where this can be a GLG, good leaving group, GLG. And we're now ready to go into the second step where the halogen can come in and attack. And this gets kicked off. And either we can have SN2 or SN1 conditions. When do we see SN2? Well, if you take that protonated OH, protonated because you gave up the proton to the OH, and you have still the X minus left. If you've protonated that OH and you've made water, if you circle the carbon that it's connected to, you can determine whether that carbon is primary, secondary, or tertiary, having 3 carbons off of it. Just by circling that carbon, how many carbon-carbon bonds do you cut? Well, if we only cut 1, it's a primary ROH, and we tend to see SN2 reactions. If encircling this carbon, we have 2 R groups that are present, just sort of saying these can be either hydrogens or carbons. If we have 2 carbon-carbon bonds, secondary ROH, we see an SN1 reaction. If all 3 of these R, R prime, R double prime are carbons, then we would have a tertiary ROH that's been protonated, and we will see even faster SN1 reactivity. So SN2, SN1, SN1, and we're going up in speed as we move left to right. Now let's go to the lower hemisphere in green, lime green. This side is where we have this alcohol protonated in an environment where we have no halogen-containing acid. Maybe more common to see nitric and sulfuric acid used for this, and you usually are using a higher temperature. Higher temperature, maybe 100 to 140 degrees to drive the reaction, degrees Celsius. So we tend to have a little bit of heat added to drive this reaction. If it's a primary carbon here that's off this OH, we tend to see E1-like reactions, and we'll get into what that means here in a little bit. If that's, again, secondary compared to going straight up where we had a halogen, where we don't have a halogen, sulfuric acid, we're going to see an E1 reaction. And then last, if it's should be tertiary here, tertiary. If this is a tertiary, we have an even faster E1 reaction. So again, going in greater speed as we have more substituents around this carbon that are alkyl groups. All right, so we'll flush this out, but this is just a nice rubric overall to give you the general trends for how things go. If we have an alcohol that in acid, either hydrochloric, hydrobromic, or whatever, or in sulfuric, we protonate the oxygen in the OH, so getting us to this center point, and then we ask what kind of acid do we have. If it's halogen, we start thinking substitution. If it's non-halogen containing acid, we start thinking elimination. Hope that helps. Let's take an example. So let's take a primary ROH, and let's consider a strong acid that's non-halogen containing, so non-HX, we'll just say. So it has the ability to protonate the OH group. So let's go ahead and go south here first. We're going to have the E1-like mechanism we're going to talk about first. And this is usually at higher temperature. We'll look at the low temperature later, but let's go south. So we take our proton, because we have an acid, a strong acid, and we have to protonate somebody. Just pick one of them. So I picked the one here on the bottom. We have now a GLG. I may want to circle that carbon. GLG, it's a good leaving group. We're just tagging it as such. This carbon is indeed primary. If I circle that carbon along with the water molecule, I cut only one carbon-carbon bond. So it is a primary ROH. So we look back to our rubric, and we'd say, oh, primary ROH with non-halogen containing acid, E1-like. Let's push that. What happens here is as this is breaking away, water is going to break away. We don't stabilize, we can't have a primary carbon here that's positive. You can't have a primary carbocation. What we can do is treat it as if it forms, and while it's forming, we get a rearrangement. The hydrogen here, hydride, is sliding over as this is coming off. Now it really happens, of course, at the same time, but if you need to, you can consider this water to come off first. Primary carbocation would be then satisfied by a hydride shift, and we'd have shifted to a tertiary position. That's the E1-like part of this reaction. Now we need to finish the reaction, or that's the rearrangement. Now we need to finish it because we're still at a carbocation. We need to go ahead and finish this E1-like reaction. We've already kind of covered the like. It's the hydride shift has occurred at the same time water's coming off. So what do we do? Now E1, this remaining alcohol or something in solution as a weak base, can come in and attack the beta protons. Remember, that's what the E stands for, is the beta protons. So we can attack beta protons at this position, but I've already shown this one here, so I've highlighted it. There's another one off of this carbon, so there are 3 other protons, or a total of 4 protons at the beta positions. So we can just kind of draw that E1 part of the E1-like reaction, and we get the alkene. That's what you get when you have E1 reactions of an alkyl halide or alcohol. We get the alkene. And we have the H plus that we tore off from this, using this oxygen and the other alcohol, or it does not have to be the alcohol that does this. It can be water in solution, the sulfate anion. The point is we've regenerated this catalytic proton. I guess I have my charge here. We've regenerated the catalytic proton that can be given back to the solution, aqueous or whatever, can go back to the solution and protonate another OH, and we can roll this thing round and round, and round it goes. So we only need to have a catalytic amount, because I've regenerated this hydrogen that I showed initially in gray here. We replaced it. It's not lost. We haven't lost any concentrate. I haven't lowered the concentration of free protons. So it can be given back to solution, and we can go again. Alright, so that's high temperature, E1-like reaction of primary alcohols. We get an alkene, and we, of course, regenerate our acidic protons, so it's catalytic conditions. What if we have low temperature? Well, low temperature, we need to go right to the oxonium ion, and we do the same thing we did before. We know we have a primary ROH, and we know it's, E1-like at high temperature, but what happens in low temperature? So if it specifies in a question that you have low temperature, primary ROH, and a strong acid that's non-HX, start thinking SN2. Since there's accessibility, we can have that other alcohol molecule in solution come in and attack the carbon, not the beta proton, before this comes off, but after it comes off. This was coming off, and then we had I guess we considered the rearrangement, and then we came in on a carbocation and drew our products. But we can, at lower temperatures, not coming off so quickly, giving it more time to find this carbon, we can have an SN2, a competing SN2 reaction. Again, at lower temperatures, this is favored. Now notice, if that comes off, our water molecule comes off, we still have a proton here that would be off this oxygen that would now have a positive charge, because it went from owning its 2 electrons as a lone pair that it's using for the attack to sharing. Those are right here. So it has a positive charge. So what I'm trying to point out is that either way you go, low temp or high temp, we have a catalytic proton that is going to be regenerated. So this can be taken off, put right back here, and we can keep on going. So low temp favors SN2, high temp favors E1 like, where the E1 like just came into the picture because we have water coming off if it's high temperature, while the hydride from a neighboring carbon is sliding over, or some sort of carbocation shift can occur. All right, now let's finish with discussion of halogen-containing acids and those Lewis-type acids. So just 2 more slides, and we're done. So we can take a primary, there's 3 more, let's go quickly here. Primary ROH, now a halogen-containing acid. Now we're thinking substitution, not elimination. Since it's primary, we're thinking SN2. So I can have, I'm going to go ahead and just show my intermediate here. We can have protonation. From the reagents, I protonate this oxygen. I would have this plus the Cl minus left in the solution after these 2 react as intermediates. And because this is a primary ROH that's protonated, we know the rubric said it favors SN2, so we have the chloride come in while this is kicked off, and we get our products. Pretty straightforward, not too involved, but you just need to know where you're going. Know that your tags are present. We know this is a primary ROH. At this point, we know it's a primary ROH. We tagged it after it had the proton. It doesn't matter where you tag it. At this point or at this point, it's a primary ROH. This is a halogen-containing acid, so we knew SN2 chemistry. After protonation, we have SN2 chemistry. Halides are not basic, but they are polarizable. That's what's giving us a little bit more reactivity as a nucleophile hitting a carbon than as a base. They are not basic. This is important. They have power in their polarizability. That is, their ability of electrons to morph in their shape in the valence shell, so they can attack, and carbons that are maybe a little more hindered, they can do that a little more quickly. Secondary, tertiary ROHs and HX, SN1 is favored. Go to the carbocation, and if you have a carbocation, you can have rearrangements. So we don't see that with SN2, but remember, if you go to carbocation, make sure to watch for any possible rearrangements after you form the carbocation. Now I've just drawn a mechanism involving a tertiary ROH and a SN1 reaction. We know we protonate. That's first, and I just flipped this over. We have our oxonium ion where we have the GLG, good leaving group. And we have a tertiary ROH. It was still tertiary over here, protonated form, tertiary ROH. So we know what to do. It's an E1 reaction. Sorry, chloride, sorry, SN1 reaction, because we have not a basic anion, but a very polarizable anion. It's the halogen-containing acid. We need to think substitution. So this comes off. Since it's SN1, the carbocation has to be formed. And there's no rearrangement. It's a tertiary carbocation, so there's no chance for rearrangement. We just have the chlorine then come in, part of the SN1 reaction. Either this side or this side, it doesn't matter. There's no chirality center, and we're done. I've just shown the energy diagram for the reaction where protonation, carbocation, so protonation, protonated form. That's here. Oxonium ion, we have the carbocation. That's here, and then our final product. So 3 steps. Remember Hammond's postulate, whatever is going to stabilize the carbocation lowers the energy of this step, because if we stabilize the intermediate, we stabilize the transition state that's nearest that intermediate. All right, we're running out of time, and I don't want it to be too long on this slide. I just want to say, if we have I have a Lewis acid, phosphorus tribromide, thionyl chloride. Typically, if those are used with primary or secondary ROHs, you tend to have SN2 reactions. Not always, but you tend to have SN2 reactions. And a little bit of that is due to the fact that you typically have in these no H2O. Kind of go together here. Not always SN2. There are some exceptions, but if we have thionyl chloride and usually some acid scavengers or something like that, you tend to see more SN2 reactions, and you cannot have water present with these at all because these are reactive, very reactive with water. So you tend to get substitution in an SN2 manner to make the alkyl halide. Now, I've not shown the mechanism for this. You're just going to need to know that after this reacts with the phosphorus, the oxygen in the first step either starts bonding to the oxygen, or in this case of thionyl chloride, starts bonding to the sulfur. We start making this oxygen a better leaving group, not by protonating it, but having it react with a Lewis acid site, either phosphorus or sulfur. And I don't have the mechanism for this, and I just want to go quickly to what your products would be. This starts to make a phosphorus oxide, sulfur oxide, that makes a good leaving group, and we can have substitution, where the chlorine can be kicked off, come back around, and knock off the oxygen, or the bromine can get kicked off, come back around, and knock off the phosphorus oxide. So we can get this substitution. It's not a very nice discussion and a very thorough discussion, but just remember to go right to the alkyl halides. And it's typically an SN2 reaction. So if this had been a secondary that was an R center, it goes to S as a chirality center. So remember, it's typically SN2, not always. Now, there is another type of Lewis acid that we can use as a tosyl chloride. Tosyl chlorides are just a type of sulfonyl chloride where we have a sulfur, it's like a sulfuric acid group, where we have a chlorine-sulfur bond that's very reactive, and this is a methyl group here. So that's the structure of tosyl chloride. That reacting with an alcohol, we tend to stop at the sulfur-oxygen bond formation. So we take this sulfur, this gets attacked by the oxygen just like this was attacked, and we kick off the chlorine, and it bonds to that H that was here, and we get HCl. So we get this forming HCl. Now this is called a tosylate. We have now a tosylate shown here. This tosylate, we can stop at this point and have, I guess, a great leaving group where something can come in and kick this off. So we can stop at the tosylate, and that can allow for some further chemistry. This doesn't stop. You tend to, with phosphorus tribromide, thionyl chloride, have a complete reaction, complete removal of that oxygen, so it's replaced with a chlorine. Or in the case of phosphorus tribromide, a complete removal of the OH and replacement of that with bromine. This is a little bit different. We don't kick this oxygen off. It stays on. Stays on. So no inversion, no SN2 at this point. It stays on. The oxygen does not come off. The only thing we've really done is we've replaced the H with the tosyl group. That gives it an ability to go into strong base conditions and act as a leaving group. We can't just substitute this OH off if we go into strong base conditions, because that'll just grab the proton. So that's why we tosylate, is that we can go on into base conditions and have this get kicked off. This is a long video. I hope that's provided you with some discussion, understanding. Very poor, just a surface coverage of these Lewis type acids, phosphorus tribromide, thionyl chloride, tosyl chloride. I know that, but I hope you have been able to catch a little bit more of the types of reactions Bronsted acids will give. A little more discussion on those. So we've looked at these alcohols in reaction with Bronsted acids, either halogen containing or non-halogen containing, and we've looked at these reactivities of alcohols with Lewis type acids, thionyl chloride, phosphorus tribromide, and our tazochloride. That's it. Bye-bye.